All right, so we'll finish up graphing today, which is section 2.4, just the last part of it, and that's on period changes. All right, so period change, just to kind of show you what that looks like first. Okay, we've done the shifting left and right. We've done shifting up and down. We've done stretching and compressing up and down. The only one we haven't done is stretching and compressing horizontally. All right. So consider that like your starting point. If you take the frequency and raise it up like I just did, that causes the wave to compress. And if you try to bring it back down, if it lets you, now it's starting to stretch. So that's stretching it, and that's compressing it. All right, so we'll take a look at what some of those sound like in a little bit. But that's the idea of what we're doing today. Stretching and compressing on the x-axis. So back here. So, first thing we got to figure out is, if you're looking at a problem, how do you know if it's a period change? Well, period change is when you have sine or cosine, and you multiply by a number in front of x. Okay, your book just uses the letter omega to represent putting a number in front of x, but in general, omega would just be a number. It could be a 4, it could be a 2, okay, any number you want in front of x. That's a period change. So what we'll do eventually is I'll show you kind of an example, and we'll look at everything. Okay, we'll identify where's the phase shift, where's the period change, where's the vertical shift, where's the amplitude change. So those are the 4 things you want to know where they are. Okay, but that's where a period change is. Number in front of x. All right. So depending on the number you put in front, you can either stretch it or compress it. Does anybody have a guess what? Let's look at the 4, sine 4x. If you graph sine of x and sine 4x, what do you think the 4 is going to do? Is it going to stretch, or is it going to compress? Yep. Ryan?
Is it going to stretch it?
Okay. Could stretch it. Or, yeah, what else? What were you going to say?
If it was a negative, would it compress it?
Negative would cause a flip. We're not going to do any negatives with these today. So the number in front will always be higher than 0. Okay, so negative would cause a flip, kind of like the negative did yesterday. It'd be a little different, but we're not going to look at it. So Ryan thinks it's going to stretch. You said stretch?
Yeah.
Anyone think it's going to compress? Casey, you're the only one? Okay. Well, let's graph it and see what happens. Okay, rather than do it by hand, I'll just use this to do it quick.
It's going to compress it.
So it's sine x and sine 4, sine 4x, x. All right, let's take a look. So there's, that's the original. And the one you're going to see in red, that's the new one.
I was right.
You were right, yeah. So it compressed. In fact, if you look at it, make it a little bigger, just focus on the section that ends right there and starts right there. Just look between those 2 lines. That's one cycle of the blue wave. Okay. Starts, goes up, goes down, and goes back. Can anybody see how many cycles of the red wave you get?
Oh, so it's over, whatever the number was before is going to be how many cycles is going to be in a period?
Is it 4?
Yeah, it's 4. Yep, you get 4 cycles. It's going up, down, and back up, down, back up, again, and again. So it's doing it 4 times. So basically what that 4 did is it compressed it 4 times as much. So you get, that's what it looks like. So any question on that? What do you think, just move this out of the way. What do you think the 1/2 would do?
Compress it by a half.
It would compress it if it was bigger than 1. So the one we just did is a compress.
So this
So 1/2 is going to stretch. And what it's really going to do is stretch it out twice as much. Okay, that's basically what happens. So the key idea is if the number in front is more than 1, compress. Which you might think it's kind of the opposite. You think, well, wouldn't a big number make it bigger? No, this one's the opposite. Big number compresses it. Small number stretches it. Okay, so let's look at that. So we already said how it's stretched. Okay, it's stretched or compressed along the x-axis. And exactly how is it stretched or compressed? Right here. If the number in front is bigger than 1, compress. The bigger it is, the more it compresses. So if you graph sine 2x and sine 20x, 20x is going to be even more compressed. If your graph is between 0 and 1, the number in front of x. Okay, this is where I said you're never going to have a negative. Okay, so as long as if it's between 0 and 1, that will cause your graph to stretch. The closer it gets to 0, the more and more it stretches. Okay, so if you had like sine ½ x and sine 1/10 x, 1/10 is closer to 0. That's going to stretch out even more than the other one I said. Any questions on that one? All right, so we've kind of already narrowed this down from the different things we've done, but how do you think we're going to hear that? If we stretch or compress horizontally, what would happen to the sound? It's going to change the pitch. It's the only thing we haven't really changed yet. Okay, so if I play this sound, it's about 464 hertz. Just give my speaker a second. That's what you hear. Turn down a little bit. As I start to bring the frequency up, that wave is going to compress. Okay, now this is 2,342 hertz, or you could say 2.3 kilohertz. Okay, so it's starting to get higher pitch. You might perceive that a little bit as a change in volume, because the higher the pitch gets, it does start to get harder to hear. So sometimes I have to turn it up more to be able to hear it. All right, but that's still nowhere near where we're capable of hearing. So this is up around 6.2 kilohertz. Okay, it's getting higher pitch. Does anybody know the limit, like how high we can hear? If you had perfect hearing. Anyone have a guess? 10, so 10 kilohertz or 10,000 hertz. All right, well, let's try 10 and see, roughly see what it sounds like.
That's a big compressed.
That looks cool.
It's pretty close, so it's about 10,000. It's definitely high pitch, but we can still hear higher than that.
20,000.
Yeah, it's about 20. So as I start to drag it up, I'm just going to turn it down a little. As I start to drag it up, so it's getting higher. It's 12.
Oh no.
It's 14 kilohertz.
I don't like this.
16 kilohertz. 17. 18. It's about 19 kilohertz. And now we're up almost at 20.
I can't hear it.
I stopped hearing it at 7.
Yeah, at some point you'll stop hearing it. For me, it's around 14, between 14 and 15 kilohertz.
I got
I stopped hearing it, Mr. Hager.
I can't help it. It's what happens
I
to.
stopped hearing it at 10.
It's what happens to humans. You stopped hearing it at 10? Oh, well.
Moved it up from 6.
I can hear it up to like 19.
So right about there. Yeah, I can definitely still hear that pretty well.
Yeah, I heard.
You start to lose it, and then kind of going the other way if we stretch it.
The graph looks really cool.
Yeah, it's just super compressed. It doesn't even know how to do it. So what kind of sound would that be?
Really low.
Very low. Like
Yeah, that's very low. In fact, my speaker's not capable of producing a frequency that low. The lowest, no, you just won't really hear anything. You won't really be able to do it. The lowest it can do is 45 hertz. So turn it down a little bit. So that's 45 hertz.
Oh, I like that.
That's awesome.
That's
It's
cool.
pretty low. And
Makes
we
me feel weird.
we talked about certain things about like how different objects vibrate at different frequencies. It's called resonating. And in here, did I play the 57 hertz? So we can do it again. But 57 hertz is exactly where something in the ceiling somewhere
Oh yeah, you did play that.
is resonating. Right at 57, that's where you'll hear it. Maybe a little bit there? No. Maybe a little volume. There you go. If I back it down a little bit,
What if that just exploded one day?
I'd be in trouble. But just by changing it a little bit, 56, I don't really hear it. 57, 58, I don't hear it. 57, I do. So different objects resonate at different frequencies. Okay, so that's the effect of changing the stretching or compressing horizontally, at least as far as sound goes. So when you stretch or compress it horizontally, what you're doing is you're changing the period. Let's consider that the normal period. Starts here, ends here. Does anyone remember from Tuesday what the normal period is? How many degrees?
2 pi, 360 degrees.
Yep, 2 pi radians or 360 degrees. So normally for your graph to complete one cycle, it has to do 2 pi radians or 360 degrees. Well, if you stretch or compress it, now you're changing the amount of time to complete one cycle. If you want to figure out how much time is it taking to complete one cycle, that's the formula. Okay. The book uses T for period, so that's what I did. So the period is T. And the formula is 2 pi divided by omega, the W-looking thing. Right, so the omega is just the number in front of x. All right, so let's try a couple problems with just using that formula. Okay, so here's a problem that's a period change. Okay, sine 2x. And I'm going to find the period of it. First of all, did this graph stretch or compress? It compressed. So if the normal period is 2 pi, I should be expecting a smaller number, okay? Because this period is compressing. So let's find the period. So in my fraction, 2 pi always goes in the top. What goes in the bottom this time?
2.
Yeah, the number in front of x. So the period is now pi. Is that a smaller number than 2 pi?
Yep.
Yep. So the period it's faster here. You can think it's oscillating more frequently than the original. All right, let's try this one. Cosine 5x. Okay, be careful. Don't tell me the period is 5. 5 is one of the numbers you're going to use to calculate the period, but the period of that is not 5. Can someone give me the fraction? What goes in the top? What goes in the bottom? Yep.
2 pi over 5.
2 pi over 5. There's your period. That's even shorter than the last one. The last one I took 2 pi and divided it in half. This one I took 2 pi and divided into fifths. So it's an even smaller, more compressed period. Right, let me try one more. What's going to happen with this one?
It's gonna stretch.
It's going to stretch. In fact, it should stretch 4 times as much. So if the original period is 2 pi, you probably could think quickly what that should be. But if you're not sure, let's just do it out. This time, I'm going to put 2 pi as a fraction because I'm going to have a fraction in the bottom. So 2 pi over 1. over 1/4. Okay, how do you divide when you have a fraction over a fraction? Yep.
You multiply with the reciprocal.
Okay, we're going to take what's in the top, and exactly what Steph just said, you're going to multiply by the reciprocal. So what's the period here?
8 pi over 1.
Yep, 8 pi over 1, or you can just put 8 pi. So now the period is a lot bigger. It's going to take a lot more time for the graph to go up, go down, and come back up again. Right? Stretched it out. Okay, so any question on how you calculate the period? Right, so there'll be some questions on the test, but that's all you have to do. You don't have to graph this. Just find the period. What if let's go back to the top one. What if I took this one and did a +6 on the end? How would that affect the period? Right?
Wouldn't it just shift the whole graph like
16.
6?
Yes, it would shift it up 6. So how does that affect the period? It doesn't. That had no effect on the period at all. So you might see a problem with other numbers in it that have nothing to do with the period, like a shift up 6. How about if I did this? 3 times all of that. How would the period be affected now?
Still wouldn't.
It wouldn't. What does that 3 do? It does affect something.
It shifts it to the left or right. I forget which one.
Not this one. That'd be a phase shift. Phase shift would be if you had something like this. That would be a shift left or right. But the 3 does do something else. Yep.
The amplitude.
That affects the amplitude, changes the height of the wave. Okay? So if you're finding the period, don't worry about any of the other numbers. Just focus on the number in front of x. That's the point. So how do we figure out the 5 points that are going to go in our table? Okay, step 1, always figure out what's going to stay the same. Brandon, what's going to stay the same if you're going to stretch left and right? What's going to stay the same?
The y.
Yeah, the y's. You're not doing anything up and down in this problem. Unfortunately, the y's are the easy numbers to work with. But we can't work with them with this kind of transformation. Okay, they stay the same. So if the y's are going to stay the same, x's are going to change. There's a couple different ways you can find the new x's. I'm only going to show you one way. The way that I'm going to show you is a good way to do it some of the time. The other method is a better way to do it some of the time as well. Both methods work all the time. It's just which one is faster. But I think I'm just going to stick with showing you one way to do it. All right, so let's think of sine and cosine. What's the first x value in the sine and the cosine table? They're the same. It's 0. Now let's say you take 0 and you stretch it. Okay, let's double it. What do you get if you take 0 times 2? Still 0. All right, let's try compressing it. If you take 0 and multiply it by a half, what do you get? You still get 0. So if you have your first x coordinate starting at 0, no matter how you stretch or compress it, it's still 0. Always. The only time that that wouldn't be true, which won't apply to any problems you're doing in this class, is if you did a phase shift first. Because if you shift something left or right, the first coordinate would not be at 0 anymore. It would be shifted. So then the method I'm showing you wouldn't work. But you're never going to have a problem that has 2 transformations in the same graph, so you don't have to worry about what I just said. All right, so we know where our graph is going to start. It'd be nice if we could figure out where it stops. How do we figure out the length of the period? How far away the last dot would be? Yeah?
Do we multiply each coordinate by the period?
So there's a different way to think about it, and that has to do with a different way of thinking about it. It would actually be the reciprocal, multiplied by the reciprocal. I'm going to avoid mentioning that again, but that is a different way to do it. What's the formula we just had that tells you the length of a period?
2 pi over the
Omega.
Omega, yeah.
Yep. That formula that Ryan just said tells you the distance from here to here. It tells you how far away one cycle is. So if you want to find the very end point of the cycle, use the formula we just had. 2 pi over omega. And now, once you have the beginning and the end, everything else is easy because it's all equally spaced. So, if you had the first coordinate and the fifth one, what do you think you could do with the first and the fifth to find the one in the middle, the third? Keeping in mind that everything is equally spaced.
I was going to say average them.
Yeah, average them.
Oh, okay.
So like if the first coordinate is 0 and the last one is 8, well the one in the middle would be between 0 and 8, would be 4. Okay? So to find the middle, or the third coordinate, average the first and the fifth. And just a reminder, average means you just add the two things up and divide by 2, because you're averaging two things. Okay, that gives you your third coordinate. Now, how do you think you could get the second coordinate? Well, Tyler, you found how you get the second coordinate? Keeping in mind it's equally spaced with everything.
My length of first one and then the third one.
I agree. You want to do something with the first and the third one, but don't multiply them together. Just take the first and the third one and blank them. Average. Yeah, just average them. So the second coordinate is the average of the first and the third. And then what do you think the fourth coordinate would be?
The average of the third and the fifth.
The average of the third and the fifth. Okay, this idea of averaging to get the x coordinates, it's one way to do it. It's not the only way. But it kind of reinforces that idea that everything is equally spaced because averages are always the number right in the middle. So it just kind of emphasizes that idea. Okay, sometimes the x-coordinates are going to be very nice numbers. Okay, very easy to work with. Sometimes you are going to have fractions and have to find common denominators and that stuff too. It depends on the problem. So any questions on how you find the coordinates? And you pretty much have to do them in that order. You've got to do the first one and the fifth one. Then the middle. Then you can do the second or the fourth one. It doesn't matter.
So the first is always going to be 0, 0.
In the kind of problems I'm giving you, yes.
Okay.
In general, though, like in the world of math, no. But in your world of math, in this room, yes.
And the fifth coordinate is like just the answer of t equals.
Yes. For the kind of problems I'm giving you, again. Yep.
Can you scroll?
Okay. So third coordinate, average 1 and 5. Second coordinate, average 1 and 3. Fourth coordinate, average 3 and 5. All right, so we'll try an example. Okay, everybody good with the steps? Okay. All right, so let's try this one. Y equals sine 2x. Now that you know all the transformations, the first step on the test is going to be to figure out, is this a phase shift, a period change, what is it? Okay, so we know it's a period change because that's what we're doing today. But can somebody tell me why? What makes that a period change?
Why aren't there parentheses around it?
You don't need them. Just like if you were going to write like 2 plus 3, I mean, you could throw parentheses in there if you wanted. You could leave them off. It's just one of those cases. It doesn't really matter. The only time you'd want to put parentheses, Ryan, is if you had something else added to it. Because now you want to be very clear, is it this or is it that?
Okay.
Big difference. All right, so hey, anyone think they can tell me what kind of, why it's a period change? I know, yeah.
Number before the X.
Yeah, you're multiplying by a number before X, exactly. So do you remember in a period change, what stays the same?
The X's or the Y's.
The Y's. Right? We're going to change all the X's. The Y's will stay the same. Which kind of stinks because the Y's are easy numbers to work with, but we can't work with them for this problem. Okay. First, X value. So always going to be 0 for the kind of problems you guys have. Once you get the first X value, what's the next one you want to get?
The last one?
Yep, the last one. So then we can start averaging. What's the formula to find the last one?
2 pi over omega.
Yep, 2 pi over omega. We already did that earlier. What's 2 pi over 2?
Pi.
Pi. Okay, what's halfway between 0 and pi?
Pi over 2.
What is it?
Pi over 2.
Yep, pi over 2. Basically, anytime you average something with 0, you just take half of it. If you're averaging two things and one of them is 0, just take half. What's half of 0 and pi over 2? What's halfway between them?
Pi over 4.
Yep, pi over 4. And now the last one, you might need to do that one out. So we're going to average pi over 2 and pi. How do you average two things again? What do you do with them? Add them up. Add them up. And dividing them by 2 is the same as multiplying by a half. Same thing. So I'm just going to add them up and then take half of it. Okay, to add these up, what do I have to have first? Step? Common denominator, which would be 2. So the first one is fine. Second one, you're going to have to double what's in the bottom, double what's in the top. Okay, pi over 2 plus 2 pi over 2. How much is that? Oh, Colt?
3 pi over 2.
Good, 3 pi over 2. And now, to take half of it, just multiply by a half straight across. 3 pi over 4. So, looking at it like that, does it look like there's a nice pattern in the x's?
No.
No, there is a pattern, but it's not obvious. If you wrote it like this, 0 pi over 4, 1 pi over 4, it's 2 pi over 4, 3 pi over 4, we already wrote it that way, and 4 pi over 4. That's the pattern. The reason you don't see it is because once you reduce, it kind of hides the pattern. Right? But everything there is equally spaced, and I just proved it to you. Okay. Any questions on that? So since everything is equally spaced, you can use that to label your x-axis. That's the only condition when you're labeling x-axis and y-axis. Be consistent with how you label your gaps. Okay? Be consistent. Okay, so pi over 4, pi over 2, 3 pi over 4, and pi. If you really want to label it 1 pi over 4, 2 pi over 4, 3 pi, 4 pi, that's fine. I wouldn't take off if you labeled it that way. But I just reduce it. Okay, now our y's, 0, 1, 0, negative 1, 0. Okay, also, if you want to move your labels down a couple inches, that might have been a good idea here. But again, that's okay. Okay, so as far as arithmetic goes, that's about as bad as it gets. Okay, from these kind, it only gets better, easier to do. Any questions on that? Okay. Did that graph stretch or did it compress? Yep, it compressed. Normally for the graph to do one full cycle, it would have to go all the way to 2 pi. Now it's doing one full cycle in half the time, okay, pi. All right, let's try this one. Cosine 1/4 x. So Cade, what kind of transformation is this one?
Couldn't tell you.
What are we studying today?
That's a good question.
What's the title of the section?
I didn't write that down.
Somebody help him out. What's period change? Okay, it's a period change.
Yeah.
Period change. CC, what column stays the same? Always your y's. Can somebody else remind me for my y's for cosine?
1,
Yep.
0, negative 1, 0, 1.
Perfect. So cosine is the table that it reads forwards and backwards, the y column, the same way. All right, now my x's. For any period change, x's start
0.
0. And we already did this number earlier in the notes. We did 2 pi divided by 1/4. And does anyone remember the period we got?
8 pi.
It was 8 pi. What's halfway between 0 and 8 pi?
4 pi.
Halfway between 0 and 4?
2 pi.
And 4 and 8.
6 pi.
That was easy.
Yeah, this time the numbers worked out very easy because there were no fractions. And those are all equally spaced. I think that's very obvious to see. They're all 2 pi apart. So that's how we'll label our x's. 2 pi, 4 pi, 6 pi. Just squeeze it in if you can, 8 pi. For today, every y value is going to be 1 and negative 1. That's never going to change for today. All right, so we've got 1, 0, negative 1, 0, and you always end with the y value you started with. And that's it. So did this graph stretch or compress?
Stretched.
Yeah, it stretched a lot. Normally you would have done a full cycle by the time you hit 2 pi. At that point in this graph, you're only a quarter of the way through the cycle. So you have to go a lot further to get the whole thing. 4 times as far.
Do we have to, I'm sorry, do we have to skip numbers for that? I mean, like skip lines for this one or no?
No, you won't have to skip. That usually only happens with a phase shift. I mean, you could skip, depending on how you label it, but I wouldn't. I would do it this way. Any other questions on it? All right, let's try this one. So at first, when you look at that, you might be like, well, it looks a little tricky, right? You got a different kind of number in front of x. But once we start this one's actually going to be the easiest arithmetic one we've had yet. Okay, x's are going to be very, very simple. You'll see why shortly. All right, so we already know it's a period change, right? Y's are going to stay the same. We already did y's for sine. So just fill those in. We did the y values for sine two problems ago. Okay, first x value?
0.
Yep, 0. Now let's find the ending x value. It's going to be 2 pi. And what are we going to divide by?
Pi over 2.
Pi over 2. How do we divide by that again?
We do the reciprocal.
Do the reciprocal. So 2 pi over 1, what's the reciprocal of pi over 2?
2.
And when you multiply it together, what happens?
We get 4 over pi. No, the pi's cancel. Oh, I meant 4.
Just 4. Yep.
Wait, so what do you do with that?
Well, that's where it ends. That's the fifth. That's the fifth value. You put it right there.
Can you graph that though?
Yep. This time the numbers are going to be very, very nice. I'm going to be able to just label it like 1, 2, 3, 4. You'll see in a second.
Oh, okay.
So what's halfway between 0 and 4?
2.
And then 0 and 2?
1,
2 and 4?
3.
So technically you don't even need to label anything, because if you leave your graph blank, I'm going to assume you're going by ones. And in this problem, I'm going to go by ones. Any question on that? So don't get, kind of like nervous at first. You look at that number in front of x and think it's going to make everything worse. It actually made the numbers a lot better. So even though I said you don't have to label, I'm still going to label. 1 and negative 1. And now just put in your y's. 0, 1, 0, negative 1, 0. Now, normally the period would have gone to what number? How far?
2 pi.
2 pi. So that's 3.14 times 2 roughly. If you double 3.14, that's 6.28. This one's only going to 4. So it compressed it a little bit. Not a lot, but it did compress a little bit. Okay. Any questions on that?
No.
Okay. Anything else on period change before I show you some different stuff with sound?
I can show us the phone things then.
I hope so. It's going to be one of the things I try to show you. Other factors have to cooperate with me, like cell phone reception. I think it will. All right, so first thing I'm going to show you is this thing. Has anyone ever heard of that before? An LRAD?
No. Yeah.
You've heard of it?
Yeah, I've heard of it.
From my class or somewhere else?
Like History Channel or something.
They showed it on there?
Yeah.
Yeah, it stands for Long Range Acoustic Device. And you can think of as an LRAD, it's like a special speaker. Okay, it's a speaker that's kind of like this is. It's like this is a laser pointer. It's not a speaker. But the point is when you point it at something, how spread out is the beam of light that I just created with this. Like, could I use this as a flashlight?
No.
Probably not. It's not going to work well as a flashlight because it's concentrated in a very small area. Well, an LRAD is a speaker that concentrates the sound in a small area. Not as small as a laser pointer, but it might be an area that's like 30 or 40 feet across. So like, if I'm aiming it away from me, I'm not going to hear it very well from behind, unless it bounces off a wall and echoes behind me. But if there's nothing around to echo, and I aim it away from me, I'm barely going to hear it at all. Okay, so that's what this speaker does.
Would they be like speakers that somebody would use at a concert?
So you could use, they probably wouldn't use exactly this, because I don't know how good it would be with instruments. But what they do use it for is for your voices. So in order to give commands to people, like in a big crowd, they can also use it to emit a frequency that's very annoying, really kind of this oscillating high-pitched sound. And imagine like the sounds I can play in here, like hundreds and hundreds of times louder. If it's that unpleasant of a sound, you probably want to get away from it. Because if you don't, it can cause you to go deaf. So it's the kind of sound you just want to move away from it. So I'll show you a little clip about an LRAD and kind of what they've used it for. I think they say it was most recently demonstrated in like 2005 or 4. They've used it a lot since then. I haven't got a new video yet. All right, so let's take a look at that. Okay, don't play the LRAD in the video. And basically what they're going to play looks like that. That's the frequency of an LRAD. So an oscilloscope shows you a picture of sound. And that's what you're going to see. So there's a pattern to what they're playing, but it's not a sine wave. When you hear it, you'll know it's not a sine wave. It's probably going to open like 3 times now. Hold on. That's good. This video is very soft, so even though it's on 100, it's not going to be that loud.
In response to the terrorist attack on the USS Cole in October of 2000, American Technology Corporation created a device like no other. LRAD, the long-range acoustic device.
A wave of the future.
A high-tech tool developed by the military.
A high-tech sonic weapon.
Long-range acoustic device, or an LRAD.
The long-range acoustic device, or LRAD, is like an audio spotlight. When you're standing alongside of it or behind it, you can carry on a normal conversation, but get directly in its beam, and the sound becomes almost painful.
Because of its weight and size, the LRAD is easy to transport, easy to set up, and mounts almost anywhere.
Cruise passengers now barely escaping that pirate attack.
We're learning more about that stunning pirate attack.
This magnificent cruise ship attacked off the coast of Africa by 21st century pirates.
The LRAD's usefulness was most recently demonstrated in November 2005 when pirates attempted to attack a cruise ship off the coast of Somalia.
It has 26 languages and about 100 different remarks like put your hands on your head, or lie flat on the ground, or turn around and do such and such.
The system clearly enables us to enforce the Naval Vessel Protection Zone at all times.
The fact that an individual was informed of the reasonable consequences of his actions and continued to defy legitimate authority, they are personally responsible for whatever happens next.
Whether initiating communication or warding off unknown adversaries, the LRAD has proven effective more than 80% of the time and has saved countless lives in the process. From American Technology Corporation, LRAD, the long-range acoustic device.
Right, so especially in like a crowd control kind of situation, it's not a totally harmless device because it can cause deafness. But the idea is that it would be less harmful than rubber bullets or even tear gas to disperse a crowd. And it's a very unpleasant sound. There's another video which I'm going to hold off on for, well, no, I guess I can show you. It's basically a show where this helicopter pilot was flying and they're using an LRAD on the helicopter. So it's to show, has anyone ever seen the show Whale Wars? So it's kind of a show where there's like a group of people that are trying to prevent the whales from getting caught, and then there's these group of people that just try to catch the whales, kill them, and then sell like everything they can. The oil, the skin, all the stuff, because they can get a lot of money for it. So these people are trying to stop them from harvesting whales, and the guy that's kind of like preventing this, he's flying a helicopter over the ship to see what they're doing with the whales. He's trying to find out. And you'll see they use an LRAD on him. Okay, this video is a lot louder, so I'll turn down a little bit.
That's it. You can't tell if that's it or not. You can see the LRAD. That's it, guys. That's it. I was afraid it would be of a military grade. Because something of that caliber can actually cause permanent deafness. And I knew that our small boats would be getting very, very close to these ships.
Let us use the LRAD on the helicopter. They said it's just a very high-pitched noise.
That's bad, that's bad. It's just
absolute madness if you use an acoustic device on someone in your helicopter and pose it. There's absolutely no threat to them whatsoever.
They get attacking our crew with LRAD. Okay, class weapon. They're becoming really aggressive, but we have to defend ourselves.
That's just an example, a little more recent than the other video where they're using it to try to get the helicopter to go away. So the one thing about the LRAD is it's very directional. So if you fly 100 feet off to the side, you're probably not going to hear it anymore. But flying a helicopter, it's not really the kind of thing where you can just block your ears because you need to keep your hands on the controls and flying. So basically that's why you saw the helicopter fly out of the path of the LRAD. And it does have quite a range. I don't know the exact range, but it's easily from here to the trees without an issue, okay, which is a couple hundred feet, and even further. That's why it's long-range acoustic device. Like a football field. Yeah, at least a football field, maybe even further, depending on conditions. Temperature has a big thing with sound. But yeah, you can travel pretty far. Any questions on that? All right, so next thing I'm going to show you has to do with, it's called DTMF. Have you ever heard of that? DTMF? Stands for dual tone multi-frequency. Yeah, DuckDuckGo. Let me try typing it in here and actually let me go to my computer because that's a little faster. Okay, so DTMF stands for, again, dual tone multi-frequency, and that's exactly how phones work. Okay, so anytime you press a button on a phone, anytime a phone rings, anytime it's a busy signal, all that stuff, those are just frequencies. For example, here's a picture of what I'm going to play for you. That's I think it said it's what a 1 sounds like. Yeah. If you press the 1 on your phone and you had an oscilloscope and you could see a picture of it, that's exactly what it would look like. So it's not a sine wave. It's definitely a wave to it. And there's a pattern. It does repeat. I think that's the beginning. That's the end. So you could copy and paste that picture next to it and get the next cycle of that wave. But that's what it looks like. Because it's not a perfect sine wave, it's not going to sound like a constant tone. It's going to have a different kind of quality to it. And let me play it. So just go back. So it tells me the two frequencies are 1209 and 697. If you can see it, there's a little chart right here that tells you all the frequencies for the different numbers. What I'll do first is I'll just play each frequency separate. So here's 1209. And let me turn it down. I guess I should turn it down a little bit. So 1209. All right, so there's 1209. Now let me play the other part of that, which is a 697. And neither one of them separate is going to sound like a button on the phone. Okay, but now I'm going to put the two together, so you're going to hear like 1209 out of the left speaker and 697 out of the right, and your brain is going to put the two sounds together at the same time. And yes, I am. So that sound that you hear, that's when you press a 1 on the phone. Okay, or any other button. I think it's a 440 and 480 at the same time. I think you'll recognize this one. Yeah.
That's when someone calls you.
That's the ringtone. Yep. So the ringtone is just those two frequencies at the same time. If you change one of them a little bit, you'll definitely hear the difference. Like, if I just change 440 to 450, okay, just throwing it a little off, it doesn't sound right. So there's a point at which maybe you could hear the difference, maybe you couldn't. If I played 441 instead of 440, I don't think you'd hear it. Would the phone hear it? Probably. Okay? Digital equipment is very sensitive, and it can pick up a very, very, very small change in frequency. A much smaller change than you could hear, or I could hear with my ear. All right? Even a musician probably couldn't hear the difference very well between a 1 hertz frequency difference. It's so similar. So, what I can do is, if I make a call, okay, I'll call my voicemail, and it's going to say press 4 to enter your personal options, where you can change your greeting and all that stuff. Well, what I'm going to do is generate the signal for a 4. So it's going to play over the speaker, my phone's going to hear it, and then it's going to transfer it into some kind of electric signal and send that to my voicemail, and it'll think I pressed the button. So just by playing the right frequencies, my phone is going to think I'm pressing the buttons. So let me
Wait, what?
see if I can show you. What's that? Just watch.
How does that even work?
Okay, the first frequency is a 4. So let me actually get that ready. 1209 and 770. That should be loud enough. But it does have to be kind of quiet because I'm so far from the speaker that any other sounds or voice frequencies will...
Wait, will it work with mine?
Yeah, it will work with anybody that calls their voicemail. So let's just try it. As long as I have service.
First message. For 14 days. End of new messages. Main menu. To listen to your message, press 1. To send a message, press 2. To check receipt of the message, press 3. To change your personal options, press 4. To disconnect, press star. Personal options. To turn notifications on or off, press 1. To change administrative options, press 2. For greetings or recorded names, press 3. To change notification options, press 4. To exit, press star. You have one saved message. Main menu. To listen to your message, press 1. To send a message, press 2. To check receipt of the message, press 3. To change your personal options, press 4. To disconnect, press star.
It said goodbye, but it kind of cut off. But it just hung up. So just by generating the right frequencies, my phone thinks that I was pressing the buttons. Now you might be like, well, when I press the buttons, I don't actually hear the frequencies. And most of the time you don't. Like on this kind of phone, you do. Just because you're not hearing the frequency doesn't mean your phone's not generating the signal, like silently. Okay, so it can do it 2 ways. It can hear the frequency and then send the signal, or it can generate the signal silently and send it that way too. It works either way. So on this kind of phone, like with a dial tone, what I could do is, right now the dial tone's on, it's waiting for me to start dialing. If I was generating the right frequencies, it would start dialing the phone right now.
Can you do that?
I could.
You should try.
But you wouldn't even know unless, because I can't put this on speakerphone. So you would be able to hear that I'm actually doing it.
Can you put your phone on speakerphone?
This phone?
You just did that.
Well,
you
this
can
phone.
call somebody on your phone.
Oh, this one?
Yeah.
I could, but this one would work better because it has a dial tone. Cell phones don't use dial tones. They don't really work quite the same. Yeah, I had a speakerphone. That would be pretty neat. I could dial it, but the thing is, I have to dial it fast enough because right now it's doing this weird thing because I didn't dial anything. So what I might have to do is open up like 2 or 3 of those. So if I wanted to dial a number, all the frequencies were ready. Either that, or I'd have to have somebody helping me change it real fast to different frequencies. But that's basically how cell phones work. They just use frequencies. Hey, any questions on that?
No.
Alright, so the last thing I'm going to show you has to do more with music. So, does anybody play music in here?
I used to play the guitar.
The guitar? Do you remember what it's called when you play multiple notes at the same time?
What? Hit the recorder.
Like when you play multiple notes at the same time?
Oh, I don't remember. It was a long time ago.
Yeah. That's a chord. Alright, so usually when you play music, it's not just composed of like single notes. You put multiple notes together and you get chords, and you put chords together and you get a song. Well, when we play just a single note, okay, like if I play that note, okay, 12, 12, 10, or I play 12, 11, we don't really hear much of a difference between the two. Okay, our ears aren't sensitive enough. But if I bring it all the way up to like 12:29, I can hear a difference between the two. And if you play them together, you definitely hear it. So at some point, you start to hear a difference, and some point you don't. So the video I'm going to show you, this guy looks at the question, will we ever run out of music? Because there's only so many different tones you can actually hear. And there's only so many different ways you can arrange the tones you can actually hear to make a song. Will we ever run out of music? So I'm going to show you a little bit of a clip from that, and then we'll end with one other video.
Hey, it's Michael here, and the iTunes contains 28 million different songs. Last.fm carries 45 million songs, and the Grace Note database of artists, titles, and labels contains 130 million different songs. That's a lot. If you were to listen to all of the songs in the Grace Note database one after the other in a giant playlist, it would take you more than 1,200 years to complete. But since there are a finite number of tones our ears can distinguish, and because it only takes a few notes in common for two musical ideas to sound similar, will we ever run out of new music? Will there ever be a day where every possible brief little melody has been written and recorded, and we are left with nothing new to make? A good rule of thumb might be to say that if modern recording technology can't distinguish the difference between two songs, well, neither could we. So let's begin there, with digital downloads, MP3s, CDs, and a calculation made by covered in B's. Digital music is made out of bits. Lots and lots of bits. But each individual bit exists in one of two states, a 0 or a 1. Now what this means is that for any given, say, 5-minute long audio file, the number of possibilities, mathematically speaking, is enormous, but mind-blowingly finite. A compact disc, which samples music at 44.1 kilohertz, is going to need about 211 million bits to store one 5-minute song. And because a bit can exist in two states, either a 0 or a 1, the number of possible different ways to arrange those 211 million bits is 2 to the 211 millionth power. That value represents every single possible different 5-minute long audio file. But how big is that number? Well, let's put this in perspective. A single drop of water contains 6 sextillion atoms. 6 sextillion is 22 digits long. It's a long number, but the total number of atoms that make up the entire Earth is a number that is about 50 digits long. And estimations of the total number of hydrogen atoms in our universe is a number that is 80 digits long. But 2 to the 211 millionth power, the number of possible different 5-minute audio files, is a number that is 63 million digits long. It is a number larger than we can even pretend to understand. It contains every possible CD-quality 5-minute audio file. Inside that amount is everything from Beethoven's Fifth to Beck's Loser. It even contains a 5-minute conversation you had with your parents when you were 3 years old. In fact, every one of them. It even contains every possible conversation you didn't have with your parents when you were 3 years old. But it is finite, not infinite. It's cool to think about, but it doesn't come very close to answering the question of this video, which is how many possible different songs can we create and hear the difference between. So for that, we're going to need to narrow down our hunt. On everything 2, Ferris Lepidoptera made a calculation that involved some assumptions that I think helped narrow the field down in a really nice way. She took a look at the total number of possible different melodies you could create within one octave, containing any or all of the intervals we divide octaves into. Of course, sound frequencies can be divided much more granularly than that, but giving ourselves more notes might mean we could make more technically different melodies, but they wouldn't necessarily sound any different to our ears. Now, given a single measure containing any combination of whole, half, quarter, eighth, 16th, or 32nd notes, she calculated that there would be this many possible unique measures, which is a smaller number than we had before, but to put it in perspective, this is how many seconds old the universe is. Your DE's calculation is even more specific. He stayed within one octave, but instead of looking at a complete measure, he only considered the number of unique combinations of 8 notes. He also assumed that typical melodies as we know them today only contain about 3 different types of note length. For instance, quarter, eighth, and 16th, or whole, half, and quarter. To be sure, that will most likely not always be true. Musical tastes hundreds, thousands of years from now will most assuredly be different. But given melodies as we know them today, across 8 notes, over 12 intervals, there are about 79 billion possible combinations. We're getting relatively small here. I mean, under this definition of melody, 100 songwriters creating a brand new 8-note melody every second would exhaust every possible melody within only 248 years. But it's still a huge number, way bigger than the total number of songs that have been written that we know about. So you can quite safely say that, no, we will never run out of new music. But here's the rub. If that's the case, why are there so many commonalities between songs, even across hundreds of years? How come so many songs kind of sound the same? I mean, if we have more possibilities than we could ever exhaust, why is Twinkle Twinkle Little Star, the Alphabet Song, and Baa Baa Black Sheep all the same melody? My Country 'Tis of Thee and God Save the Queen, interestingly enough, are the same song. Love Me Tender is exactly the same as the old American Civil War song, Aura Lee. And a seemingly uncountable number of songs merely sound like other songs. The SpongeBob SquarePants theme has a very similar cadence to Blow the Man Down. SoundsJustLike.com is a great resource for exploring this further. It'll show you 2 songs and how they sort of sound alike. And when it comes to musical chords, it's almost as if there's no variety at all, as was famously shown by the Axis of Awesome's 4 chords. I've linked it in the description. It's worth a watch if you haven't seen it already. These guys sing more than 40 different songs using the same 4 chords.
Okay, and that's the last video that we will end with. So I'm going to pass out the homework while you're watching that, and that'll be it.